So now we're going to show that every subspace of V is a direct summand of V. And so a little bit more precisely, what that means is the content of theorem 2.34. And that is that if U is a subspace of V, then there's another subspace so that we can write V as the direct sum of U and W. Okay, and so again, this is going to be one that we are going to prove only for finite dimensional V's. Okay, so in this case, suppose that we've got a basis of our subspace U. Then by the theorem that we saw earlier that says every linearly independent subset extends to a basis, right? This is a linearly independent subset of V because, or sorry, sublist of V. So it can be extended to a basis. And so we'll say that it's the U's, and then we'll call the other ones W's. And we'll take W to be the span of these new things that we throw in order to get a basis of all of V. Okay, so now we just need to check that we have a direct sum. So we need to show, so this stands for need to show, two things. We need to show that V is the sum and that the sum is direct. And we have a lemma that says that's equivalent to the intersection of these two spaces being only 0, right? So we'll start with this first one, that it decomposes as a sum. Okay, so what does this mean? This means that for any element of V, we need to be able to write it uniquely as we need to be able to write it as a sum of something where one part is in U and one part is in W. Okay, so let's see. So we know that we've got this this basis right here, so we can expand V in terms of this basis. Oops, wrong letter. So here it is written as a linear combination of elements of the basis that we worked out before. And now all of the U's are in U. So this part right here, this guy, I can call this little U. And I can call this guy here little w. And so then this looks like U plus, whoops, U plus W, where U is in U and W is in W. Okay, so that's what we needed to show for that part. For the intersection, let's see, so we'll take something in the intersection of those two spaces, and out of a complete lack of imagination, I'll call it V again. then I'm going to need to show that v is equal to the 0 vector. So let's see. So since v is in the intersection, I know that, let's see, so v is in u. That means I can write it as a1 u1 plus am um. And also, since it's in the intersection, I know that v is an element of w. So if v is in w, then v looks like b1 w1 added up through bn wn. Okay, so I get two different representations for it. One as an element of w, and one as an element of u, right? Okay, but I also just have these two equations, and so I can subtract, and on the left I get v minus v, which is just 0, and on the right I have a1 u1 plus, and I get all those u's, and then I have minus all of the w's. And now I look at this expression that I've got right here and think about this as an expression in V, right? And so I know that this set that contains list that contains U1 up through UM and W1 up through WN, that's a basis, right? So that means that since it's a basis, all those coefficients have to be equal to 0 because it's linearly independent. Okay. So then that means that all the coefficients in this expression I have here for v, say, all those a's are equal to 0. So that means that v itself has to be equal to 0. But then that's exactly what we were trying to prove, because we were trying to show that something from the intersection has to be equal to 0. And so we're done.